15 Electric Field Part 2. The objectives of this part are: determine the electric field created by 2-point charges, define the lines and the spectrum of an electric field. But we will start by the electric force exerted on a point charge placed in electric field. For a point charge Q placed in an electric field like this charge will be submitted to an electric force F, such that F vector equal Q times E vector. So, according to this vectorial relation, we can deduce that if Q is negative, so F and E have opposite directions, and if Q is positive, F and E have same direction. Now, the characteristics of F are: the origin Q, or the point of application of F, is Q. The line of action of F, same as E. For example, if E is horizontal, so F is also horizontal. The direction of F depends on the sign of Q. So if Q is negative, F and E have opposite direction, like this. This Q is the point of application of F, or the origin of F, and F opposite to E, since Q is negative. But if Q is positive, F and E have same direction, like this. Q is a point of application, or origin. F and E have same direction. In all cases, the magnitude of F is F equal absolute value Q times the value of E. Now, for example, a point charge Q equal minus 3 times 10 power minus 8 coulomb, placed at a point A where the electric field is E equal 500 volt per meter. Give the characteristics of the electric force exerted on Q and represent this force. Now, the characteristics of F are: the origin is A, since Q is placed at A. The line of action, same as E, or horizontal like E. Direction, since Q is negative, so F and E are opposite. This is F, this is E. F and E are opposite because Q is negative. The value of F is absolute value Q times E, equals 3 times 10 power minus 8 times 500, equal minus 1.5 times 10 power minus 5 Newton. Now, for the representation, we can use this scale: 1 centimeter for 0.5 times 10 power minus 5 Newton. So for 1.5 times 10 power minus 5 Newton corresponds to 3 centimeter. Then we draw the vector F of length 3 centimeter and opposite to E, like this. Now, superposition of two fields. The electric field created by many point charges at a point is the geometrical sum of each electric field created by each point charge. So E resulting equal E1 plus E2 plus another fields, like this. Here we have E1 and E2, and we will find the resulting field. So we draw the pattern formed by E1 and E2 like this, and the resulting field E is along the diagonal of this pattern, like this. Here. Okay, so we measure the length of this vector to calculate E. We measure the value of, or the length of the vector E, and we can calculate the value of E using the convenient scale. Now, for example, let Q1 and Q2 here, Q1 negative, Q2 positive, and we want to find the field at A. But first, we have E1 oriented to Q1 since Q1 is negative, like this. Origin A and oriented to Q1. But Q2 is positive, so E2 at A is oriented away from Q2 since Q2 is negative. To determine the resulting field, that E equal E1 plus E2, we must draw the param formed by E1 and E2 like this. Then we draw the diagonal of this param, and this is the vector E resulting field. Here also we measure the length of this vector to calculate the value of E. Now, for example, for E1 equal 500 volt per meter, E2 equal 750 volt per meter, the angle between these fields is 40 degree. Calculate the value of the resulting electric field E here. So, the convenient scale is 1 centimeter to 250 volt per meter. So for E1, 500 volt per meter, we have 2 centimeter, and for E2, we have 3 centimeter. Then we draw E2 of length 3 centimeter like this. Here we draw E2 before 3 centimeter. Then we use the protractor to draw the angle 40 degree like this. Here we put a point at 40 degree, and now we trace E1 of length 2 centimeter. This angle is 40 degree. So now we complete the param here like this, and we draw the diagonal and measure the length of this diagonal here like this. We find that the length of this vector E is 4.7 centimeter. So using the scale 1 centimeter for 250 volt per meter, 4.7 centimeter corresponds to 1175 volt per meter for E. Now, a field line, or definition of field line, is a line which is tangent to any of its points to the vector E. So, a field line is a line which is tangent at any of its point to the vector E representing the electric field at this point. By convention, it's oriented in the direction of E. Here we have an example. This is the electric field, and this is the line that's tangent at any point to E. The electric spectrum is the set of field lines representing the electric field. Now we have another example for a point charge. Here we have 2 point charge, positive and negative. For the positive charge, we know that E is oriented away from Q since Q is positive. So one of this line, call it field line. And here also Q negative, E is oriented towards Q since Q is negative. So the set of this line is here, or here call it spectrum.